Picture this. It's 1995 in Havana, Cuba. The streets are filled with classic American cars from the 1950s, Chevys, Fords, Buicks, all still running despite being cut off from spare parts for nearly 4 decades. Gasoline costs more than most Cubans make in a month. The U.S. embargo has strangled the island's fuel supply, and in a small garage on Calle 23, a mechanic named Julio Alvarez is about to do something that General Motors engineers would have called impossible. He's staring at a 1956 Chevy Bel Air with a blown head gasket and an owner who can't afford the $20 it would cost to fill the tank, if he could even find gasoline to buy. But Alvarez isn't thinking about gasoline. He's thinking about the gallons of used cooking oil that restaurants dump out back every night. Oil that nobody wants. Oil that's free for the taking. What if, he wondered, this 265 cubic inch V8 could run on French fry grease? This is the story of how one Cuban mechanic outsmarted 60 years of automotive engineering, created a fuel system so ingenious it was technically illegal under U.S. patent law, and accidentally sparked a revolution that would keep thousands of classic American cars running in a country that wasn't supposed to have them in the first place. To understand why Julio Alvarez's cooking oil conversion was such a middle finger to conventional engineering, we need to travel back to 1955, when Chevrolet introduced the small block V8 that would become the most successful engine in automotive history. Ed Cole's team at GM designed the 265 cubic inch power plant to do one thing exceptionally well: burn high-octane gasoline. The compression ratio was set at 8:1, perfectly tuned for the leaded fuel of the era. The Rochester 2-barrel carburetor atomized gasoline into a fine mist, mixing it with air at a precise 14.7:1 ratio for optimal combustion. Every component was engineered around gasoline's specific properties. The fuel pump delivered 5 to 7 psi of pressure, perfect for gasoline's low viscosity. The intake manifold was designed for gasoline's rapid vaporization. The combustion chambers were shaped to handle gasoline's flame propagation speed of about 30 feet per second. General Motors spent millions perfecting this chemistry, and the result powered everything from family sedans to Corvettes. But here's where things get interesting. By 1995, Cuba had been under U.S. embargo for 35 years. The Soviet Union, Cuba's primary fuel supplier, had collapsed 4 years earlier. Suddenly, an island that had been getting subsidized petroleum at 40% below market rate was thrust into what Cubans call the special period, a nice way of saying economic catastrophe. Fuel imports dropped by 85%. Gasoline, when you could find it, cost more per gallon than the average Cuban made in a week. Meanwhile, those classic American cars, the ones that tourists love to photograph, were bleeding their owners dry. A 1956 Bel Air got maybe 12 miles per gallon on a good day. At Cuban fuel prices, that worked out to about 45 cents per mile. For comparison, the average Cuban salary in 1995 was $20 per month. Something had to be done. Julio Alvarez wasn't the first person to think about running an engine on vegetable oil. Rudolf Diesel himself demonstrated his engine running on peanut oil at the 1900 World's Fair in Paris. But diesel engines and gasoline engines are fundamentally different beasts. Diesel engines use compression ignition. They squeeze air so hard it gets hot enough to ignite fuel without spark plugs. Compression ratios of 14:1 to 23:1 are normal. That intense pressure and heat can handle vegetable oil's higher viscosity and different combustion characteristics. Gasoline engines like the Chevy 265? Different story. They rely on spark plugs to ignite a carefully mixed air-fuel mixture. They run lower compression ratios. They're designed for fuel that vaporizes easily, burns quickly, and flows like water. Vegetable oil is thick as honey when cold, doesn't want to vaporize, and has a flash point of 600 degrees compared to gasoline's minus 45 degrees. So, what was actually going wrong when people tried to run gasoline engines on straight vegetable oil? First, the thick oil wouldn't flow through the fuel lines, especially in the morning when temperatures in Havana could drop to 65 degrees Celsius. Even if you could get it flowing, the carburetor couldn't atomize it properly. Instead of a fine mist mixing with air, you'd get globs of oil flooding the cylinders. The spark plugs would foul within minutes. Carbon deposits would build up on valves and pistons. The engine would diesel, keep running after you turned off the ignition, because hot carbon deposits would ignite the oil. It was a disaster. GM's engineers would have laughed at the attempt, but Alvarez understood something those engineers didn't. In Cuba, you don't have the luxury of saying something's impossible. You make it work with what you have, or you walk. His solution was brilliant in its simplicity. First, he installed a second fuel tank specifically for vegetable oil, keeping the original gasoline tank functional. This wasn't just redundancy, it was the key to the entire system. The engine would start on regular diesel fuel, which he could more easily obtain in small quantities and which shared similar combustion characteristics with vegetable oil but remained fluid at lower temperatures. Next came the heating system. Alvarez wrapped copper tubing around the exhaust manifold, creating a heat exchanger that would warm the vegetable oil to 180 degrees before it reached the engine. At that temperature, used cooking oil's viscosity drops from 40 centistokes to about 8 centistokes, almost as thin as diesel fuel at room temperature. This wasn't some random temperature either. Alvarez had tested various temperatures and found that 180 degrees Fahrenheit was the sweet spot where the oil flowed freely, but didn't start breaking down into harmful compounds. The real genius was in the dual-fuel switching system. The engine would start on diesel, run for about 5 minutes, until the exhaust manifold was hot enough to heat the vegetable oil. Then a manual valve would switch the fuel supply over to the heated oil. Before shutting down, you'd switch back to diesel for 30 seconds to flush the vegetable oil out of the fuel lines, preventing it from solidifying overnight. But wait, there's more. The carburetor was a problem. It simply couldn't handle even heated vegetable oil properly. So Alvarez did something radical. He converted the gasoline engine to mechanical fuel injection. Using parts from a Soviet-era tractor and a Mercedes diesel pump he'd salvaged from a wreck, he created a hybrid injection system that could handle the higher viscosity and different burn characteristics of vegetable oil. The injectors themselves needed modification. Standard diesel injectors create a fine cone-shaped spray pattern designed for diesel's combustion speed. Vegetable oil burns slower, about 20 feet per second, compared to diesel's 25 and gasoline's 30. Alvarez re-drilled the injector nozzles to create a narrower, more penetrating spray pattern that gave the oil more time to mix with air before ignition. Then came filtration. Used cooking oil from restaurants came loaded with food particles, water, and various contaminants. Alvarez designed a 3-stage filtration system that would make modern biodiesel producers jealous. Stage 1 was a coarse filter made from layered cloth that caught the big chunks, bits of food, sediment, anything larger than 100 microns. Stage 2 used a modified oil filter from a Russian truck, catching particles down to 20 microns. The final stage was the clever bit. Alvarez used a centrifuge salvaged from a medical lab to spin the oil at 3,000 RPM, separating out water and particles down to 1 micron. The centrifuge was particularly important. Water in vegetable oil is catastrophic for an engine. It doesn't compress like oil, leading to hydraulic lock that can bend connecting rods and crack pistons. It also causes the oil to polymerize, basically turning into plastic, at high temperatures. Alvarez's centrifuge could remove water content down to less than 0.05%, making the filtered oil cleaner than many commercial fuels. The numbers were staggering. After Alvarez's modifications, the 1956 Bel Air could run entirely on waste vegetable oil that restaurants were paying to have hauled away. The cost per mile dropped from 45 cents on gasoline to just 5 cents on cooking oil, accounting for the small amount of diesel needed for startup and shutdown. That's a 90% reduction in fuel costs. Performance was surprisingly good. The 265 V8, which originally produced 162 horsepower on gasoline, was putting out about 145 horsepower on vegetable oil. Torque actually increased slightly from 257 lb-ft to 264 lb-ft, thanks to vegetable oil's longer burn duration, providing more consistent pressure on the piston throughout the power stroke. The engine ran quieter and smoother with less vibration than on gasoline. But here's the kicker. Emissions were dramatically cleaner. Vegetable oil is carbon neutral. The CO2 released during combustion equals what the plants absorbed while growing. Particulate emissions dropped by 50% compared to gasoline. There was no sulfur dioxide, virtually no carbon monoxide, and the exhaust smelled like a kitchen during dinner service instead of toxic fumes. In an ironic twist, this 1956 Chevy was now cleaner running than many modern vehicles. The engine wear told an interesting story. After 200,000 miles on vegetable oil, yes, Alvarez's Bel Air actually accumulated that many miles. He tore down the engine for inspection. The cylinder wall showed less wear than typical for a gasoline engine with similar mileage. Vegetable oil's superior lubricity had actually protected the engine better than gasoline. The only increased wear was on the fuel injection pump, which had to work harder to move the thicker fluid. Carbon deposits were a mixed bag. The combustion chambers stayed remarkably clean, with less carbon buildup than you'd see with gasoline. But the exhaust valves showed more deposits, a result of vegetable oil's incomplete combustion at lower RPMs. Alvarez solved this by recommending a monthly Italian tune-up, running the engine hard at high RPMs for about 20 minutes to burn off deposits. Word spread through Havana like wildfire. Within months, dozens of mechanics were knocking on Alvarez's door, wanting to learn the conversion. He taught them freely, seeing it as his contribution to keeping Cuba's automotive heritage alive. The modifications cost about $200 in parts, a fortune for most Cubans, but an investment that paid for itself in 3 months of driving. The conversions weren't limited to Chevys. Alvarez adapted his system for Ford flathead V08s,